Slide 18. As you could see in the previous slides, the great difference of the polyamides is in the property of its molecules. We see that the majority of semi-crystalline materials are very similar when the temperature is well above the melting temperature. All these materials are in an amorphous state, but when they begin to be cooled, they begin to have some differences. Part of amorphous continue like that, and part of the same material just form crystalline regions. The great advantage of the polyamides is precisely that there is still a certain attraction between the molecules in these crystalline regions that makes the polyamides have superior mechanical properties than materials commonly used in packaging. There is also a difference in favor of homopolymers respect to copolymers, and mostly a difference of bi-oriented copolymers, ultramid B40 bi-oriented appearing in the CART respect to all materials. There is also a difference in favor of homopolymers respect to copolymers, and mostly a difference of bi-oriented copolymers, ultramid B40 bi-oriented appearing in the CART respect to all materials. If we compare the bi-oriented homopolymer against other bi-oriented OS materials, for example the polyester, the difference in favor to the polyamide's mechanical properties is significant in relation to other bi-oriented materials. Slide 19. Here we can see the same type of comparative analysis of polyamides with other materials, but now in relation to the puncture resistance, a very important mechanical property, widely used for the evaluation of packaging performance. We can then check that the mechanical property of puncture resistance shows us the polyamides with performance well above other traditional materials used in packaging, such as polyolefins. Slide 20. To give continuity to everything we have been discussing, it is worth bringing the concept about the attraction between molecules of polyamide. We can notice that there is an attraction between these molecules. Only the polyamides presents a very positive effect in relation to humidity. According to what we know, the humidity is very harmful, since plastic material that contains more or less important amounts of humidity, in general, will have various more or less important problems in extrusion, like the fall in the viscosity of the material, possible reversal of polymerization, depending on the case. And according to the picture on the slide, we can have also problems in extrusion as cells or balls of humidity formation occur. While that ball of humidity occurs, a true rupture of coating material will possibly end up giving a breakdown of the film as a whole during extrusion. That would thus turn it out unuseful. Obviously, these are negative effects of humidity that should always be avoided. But the humidity, on the other hand, and at the same time, has a positive effect to extruded polyamides with materials, but only once the materials have been extruded. Why this happens? Well, it can happen because the water or the humidity begins to take position between the structures of the molecules, becoming a natural plasticizer for the polyamide film, diminishing this interaction and the contact between the structures of the molecules of the polymer, also decreasing the TG or glass transition point. Plasticizing effect has resulted in the softening and the rigidity of the material at lower temperatures. Slide 21. As we discussed, that humidity acts in those unions, in the molecular interaction, standing in the middle of the molecules of polyamide and softening that interaction to spread a little the adjacent polymer chains having that cushion between them. A decrease of this molecular attraction between the chains of polyamide will happen, which is going to have effects or consequences on the mechanical properties, as we will see below in the next slides. Slide 22. Analyzing the graphic we are presenting, we can see a clear improvement of the puncture resistance when the polyamide material is exposed to humidity in certain constant conditions. As longer the exposure is, significant improvement of the mechanical properties or puncture resistance occurs. All of this is due to the effect of the inclusion of the water between the molecules of polyamide, as we explained earlier, making the interaction between the molecules of contiguous polyamides more flexible. The effect of humidity on the puncture resistance is really significant. Slide 23. Well, we have recently seen that the effect of the humidity increases the flexibility of the extruded polyamide material. The flexibility is directly linked to the glass transition temperature Tg, above which the material behaves much better in terms of mechanical properties, rigidity, flexibility and flow. For example, in the case of a thermoformed or injection molding, the material flows better, has more elasticity, and fills better the cavity, which is one of the critical points in the conformation of a container thermoforming. Slide 24. Here, in this slide, we get to see the property of rigidity of the material as a result of the significant effect of decrease in Tg, and acting in the same way in the rigidity of the material. And we see the fall of tensile strength, which is noted as a result of the effect of humidity between the polymer chains. Therefore we see, in general, an important effect of improvement of properties by the increase of humidity. Although our focus in this event is the food packaging, it is interesting to comment on the effect of humidity on applications of injected polyamide parts. It is observed that the process of immersion in water after the injection significantly improves resistance to break parts after injection, thus changing the apparent glass behavior to a pseudo-elastomeric behavior, supporting the normal post-injection handling process during stock, packing and transport. Slide 25. Already got to discuss the whole issue of crystallinity, the issue concerning the cooling and how cooling is carried out, as well as its significant effect on crystallinity of polyamide. When we do a slow cooling, orderly growth of crystals happen, and when we perform rapid cooling, the crystals cannot grow, making polyamide have a very low structural crystallinity. Now, in this chart, we have a comparative opacity between nucleated and non-nucleated materials, both for C copolymers and B homopolymers with fast and slow cooling. The nucleated types are called with the letter N, and the not nucleated resins without the letter N. What is noticeable here is that, on this basis, we can select the type of material according to the requirements of the final material, could be both homopolymer and copolymer, and nucleated or not nucleated. The green color of the bars corresponds to a slow cooling, and the yellow color with a rapid cooling process. In the case of slow cooling, notice that both copolymer has much better optical properties than the homopolymer, therefore the opacity is less than the homo, which note the chart. Both copolymers, C33L nucleated and C33L not nucleated, have less than the B40L and B40L opacity. Analyzing green bars only, we can see that the lane materials always have lower opacity or have better optical properties than the non-nucleated or L type. Both homopolymers and copolymers. And why is this so? Well, We will now analyze the reason of this difference between nucleated and non-nucleated in relation to the optical properties. As we explained before, the nucleating works as a seed-promoting crystal formation. Crystals grow faster and smaller than the natural formation of crystals. In that way, there's less development dimension of those crystals. The material is a bit less crystalline than normal for a same cooling. If you want, the material will be a little more amorphous than normal and therefore will have better optical properties and lower opacity or transparency. And now, we are going to analyze what happens with a rapid cooling process. We note that the behavior of the materials gathered and not nucleated, seeing the yellow color graphics, is very similar. There are no great differences between the yellow bars. And note, if the cooling system is an efficient system, there is no need to use a copolymer because very similar, very good, and very low opacity transparency results are obtained with the homopolymers. You can then use a homopolymer with lower cost. Slide 26. Then after studying the properties of materials, fundamentally polyamides, let's move to the second part of the seminar, focusing on the applications of these materials. We saw that the crystallinity is affected by the speed of cooling of materials and the different types of process. We will have bigger crystals in the case of the bubble or blown film process with cooling air, and smaller crystals in the case of cast system with water cooling. We saw also that as this affected the mechanical properties and barrier, compared to polyamides, with the traditional materials such as polyethylene and polypropylene, the polyamide improves its properties in multi-barrier materials. As can be seen, the polyamide has higher melting point, and that makes the use of polyamide have to deal with higher temperatures. We know that plastic materials are not good conductors of heat, property that can be enhanced with additives. Although there are additives that improve the conduction of heat from plastics, we will not consider this type of additives here. Then, as the plastic is not good conductor of heat, conventional systems of sealing, the traditional system, presents a warm plate in the upper part and a cold mold, in general aluminum, on the bottom. The mold has a lining of rubber for container forming, but so much warming to stretch and shape the material according to the mold, as well as for sealing the container comes from the top plate with heating. Heat must pass through all the layers of plastic to deform the layers in contact with the mold and at the same time, close the container. To work with a material with heat resistance, requires to work at one higher temperature and is also going to end up getting a seal faster. Some packers used to work with only one kind of material and the coating of stamping, just to simplify the process of sealing. Here we see a symmetrical seal top with polyamide in the outer layer, to be able to work in the sealed with one higher temperature and that also is going to behave without sticking to mold and shape did not reach the temperature of fusion, which must be below the melting temperature of polyamide. In this way it is possible to make a shorter sealing cycle. Slide 27. We noticed that more or less recently many companies taking advantage of the facilities for thermoforming equipment, have invested in these technologies that involve not only the facilities but also the training of the personnel operating these facilities. Slide 28. Let's see now some structures, multi-layer films for thermoforming with 5, 7 and 9 layers. And here, we noticed that you may even work with polypropylene or with nylon in the outer layer, but remembering that the nylon is a material with higher melting temperature and higher thermal resistance, then it is possible to work with a greater resistance to heat and higher working temperatures when this nylon in the outer layer. Slide 29. Here we have some examples of 7 to 9 layers film for thermoforming application. On the right side stands the increased thermal resistance starting from materials on internal side, from polyethylene, polypropylene to nylon. Inside layer is the layer in contact with the mold. The material on external side, which is the side of sealing, is always polyethylene. In some films, due to reasons of process or application, as per example in applications of cooking of ham, it is necessary to use PAGE as an external layer instead of nylon, because there is a browning process shown by the nylon layer, due to high temperatures. Slide 30. A process that is used a lot with polyamide film is the process of biorientation. The examples we have here are cases or bags with bioriented multi-layer blown film. That process orients the polymer into the machine direction and also transversely depending on the blowing ratio that stretched the bubble or tube radially. This relationship of longitudinal and transverse stretch defines the proportion of shrinkage of the film and packing. And so we see the examples shrink bags mainly for packaging of cheese and meats. Then we see as another application casings made with monofilms layer or multi-layer oriented. In the case of the bags for cheeses for example, people have a product where the form is already defined and produced. In this case of the cheeses, the product was in direct contact with the film and thus, the risk of microorganisms ends up being less. In the case of the gut or artificial sausage case, that film has to endure the cycle because the product is packaged in cold, has a uniform mass within the gut, it is hanged and placed inside heaters for cooking, where it must resist the thermal cycle. Also, the heat resistance must have strength enough to support the entire weight of the product, and also, an increase in the thermal pressure, because the product has humidity internally that will be transformed into steam. Either it must resist high temperature, internal vapor pressure or the weight of all the product during the heat cycle. It cannot be deformed in any way, or form balls in the film of polyamide or water or gel. And to achieve that perfect superficial finishing, we should also have polyamide adherence to the meat to achieve that perfect finishing and maintain the cylindrical format. If the product is not manufactured well, a very common defect is the pear effect, forming the bottom wider than the cylinder top. This gut packing can be both single-layer and multi-layer. Some multi-layer have an internal layer of polyethylene for a good humidity barrier, due to the hygroscopicity of the polyamide. Slide 31. Another interesting application for polyamides is the inner film of dry goods or inliner application. The majority of products like sugary cereals ends up not being so demanding. The higher demand is given by the barrier to humidity. For cereals with aromas and flavors, such as chocolate, fruits, polyamide is used in a multi-layer film with high-density barrier to humidity. Polyamide comes not so much by mechanical properties, because of carton protects much product, but it is used as barrier to aromas, by the appeal of those scents in the cereal. Also, applications are being developed with polyamides materials as liners of cereals used to protect them from other solvents products during the transport of food, for example into contact with oils. also as coatings paper for the purpose of protection from solvents or oils. It is something that is being studied in Europe. Slide 32. Another application that has grown is the use of polyamide products in modified atmosphere packaging. In a good simplified form is the replacement of normal atmosphere with the normal percentage of oxygen by a modified atmosphere, with a controlled amount of gases, oxygen, nitrogen and carbon dioxide. Nitrogen is an inert gas and carbon dioxide have a bactericidal effect for the control of organisms that are present in the product. In the case of oxygen, the entrance in that atmosphere with effect primarily in the case of red meats, to maintain the red color of the meat. Hemoglobin forms with oxygen, a stronger red, more intense. While common in meat packaging, note that the darkened flesh is less attractive to consumer. Then a modified atmosphere packaging is very important because the visual appeal of the product is preserved. Polyamide enters the multi-layer materials here by their strength in the case of thermoforming, rather than by the barrier to the oxygen, because here the barrier that is used many times is achieved with EVO. Most commonly used in these applications cases are the semi-rigid forms or the rigid trays shaped. Also notice another application, modified atmosphere for cheese. What would be the advantage here? Cheeses such as mozzarella cheese has just deformation problems, even if plastic leaves are placed between the slices of cheese. Slide 33. Here we have basic structures for modified atmosphere. Films of semi-rigid bottom, has thermoformed or preformed trays, laminated with polyester-oriented by or PVC more than 170 microns. For the top, usually use a flexible material, usually laminated with bi-oriented polyester. Slide 34. This is a very interesting application that exists. They are called breathable films. These films are practically produced with 100% polyamide for a very precise adjustment to the rate of permeability. The case of the example is a vegetable that is packed with remnant humidity from its washing. If you pack a damp vegetable and a dry one, comparatively the wet one will show a yellowing effect before the dry one. The product will deteriorate much earlier. Polyamide lets that internal humidity go out, the product breathes and stays at the same time with a middle barrier to the oxygen, all of which keeps the final product better with a fresh look. Slide 35. There are many types of interesting packages, which we have reviewed here: packaging in modified atmosphere, breathable packaging, etc. But also still effective traditional containers such as pouches, flexible bags in thicknesses of 70 to 150 microns of each side of the packing. Printing and non-printing. Parmesan cheese, for example, does not need too much barrier, but there is demand for mechanical strength. For example, in solid, wedge-shaped cheeses. The challenge to the film in terms of puncture, mechanical strength, thermal resistance, break. Here it can be laminated with polyamide bi-oriented for heat resistance and mechanical strength, and also polyester biaxially oriented for resistance thermal. Slide 36. Completing this presentation, then, we have seen the polyamide properties, their characteristics, applications and different types of structures, different types of products, films. So, we can conclude that polyamides can be used in different applications with requirements for mechanical strength, heat resistance, barrier to oxygen, where an average of oxygen barrier is required. Then the polyamide is the product best suited gathering all those properties at the same time. And there is one very important thing: the conditions of processing are very important, as well as the materials, to achieve a suitable packaging. Packaging with much technology is often seen but is not the suitable packaging for that product. Often it is not enough to know which is the product that will be packing. It is necessary to know the application of the product, how product will be processed and will be applied to the packaging. You must know all the stages of the process so you can select the best combination of materials and layers, if it is the case. Our client should tell us what is necessary to be able to help you by selecting the material and suitable process of manufacture of the packaging. And very important to know that packing minimizes the loss of product, but by no means, packing will improve the quality of the product. By placing a product of inferior quality and best packing in any way, you will improve the quality of the packed product. Thank you for the attention of all of you to this webcast. I am available for contacts. Here are my phones and my email address. Well, I am now available for questions and for contacts via email.
Gostaria de agradecer a atenção de todos nessa palestra, nesse evento, agradecer a presença de todos vocês. E estou à disposição, aí temos contatos, telefone, estou à disposição para perguntas.